Assalamu alaikum, brothers and sisters. Welcome to the journey of Quest, where we quench your thirst of knowledge. Ever wondered how the different phases of matter interact with each other under various conditions of temperature and pressure? Imagine a world where solids, liquids, and gases are in a constant dynamic dance, shifting from one form to another. This is the realm of phase equilibrium, a fascinating field that has significant implications in the study of geology. At its core, phase equilibrium investigates how different phases of matter coexist at a given set of conditions. It's like a snapshot of the ongoing dance, capturing which phase a substance prefers to be in, be it solid, liquid, or gas, under specific conditions of temperature and pressure. To visualize this, geologists use phase diagrams. These charts represent the stable phases under different conditions. For instance, a phase diagram of water would show that at room temperature and normal pressure, water prefers to be in the liquid state. But drop the temperature below 0 degrees Celsius and the water would rather be a solid, ice. But it's not just about temperature and pressure. The system we're studying also plays a crucial role. A system in this context is a specific portion of matter. It can be as simple as pure water or as complex as the Earth's mantle. Each system has its components, or the distinct chemical substances it contains, and phases, or the physically distinct parts with different properties. There's also the concept of degrees of freedom, which is the number of variables that can be independently adjusted without disturbing the equilibrium. It's like a balancing act. You can change one variable, but then you'll need to adjust another to keep the system in equilibrium. So why is this important? Well, understanding phase equilibrium allows us to predict how minerals will behave under different environmental conditions. It helps us understand everything from the formation of precious gemstones deep within the Earth's crust to the processes that shape our planet's landscape. Understanding phase equilibrium provides insight into the behavior of minerals under different environmental conditions. And that's just the tip of the iceberg, or should we say the mantle. Stay tuned as we delve deeper into the intricacies of phase equilibrium studies. Imagine a system so simple, yet so complex in its interactions. Can you guess what it is? Welcome to the fascinating world of phase equilibrium studies, where we're about to dive into the concept of simple systems. Simple systems in this context refer to those in which only a single component is present, such as pure water or pure iron. Though they may seem straightforward, these systems can exhibit a vast array of behaviors due to the different phases they can exist in. A phase, in simple terms, is a physically distinct, homogeneous part of the system. In our everyday life, for instance, we encounter water in 3 different phases: solid, ice, liquid, water, and gas, steam. Each of these is a separate phase, yet they all consist of the same single component, H2O. Now, you might be wondering, how do we predict the number of phases present in a system at any given time? This is where the Gibbs phase rule comes into play. Named after the American scientist Josiah Willard Gibbs, this rule provides a simple formula for predicting the number of phases in a system under equilibrium. It states that the variance, which is the number of degrees of freedom or independent variables, is equal to the number of components minus the number of phases plus 2. Applying this to our simple systems, we find that for a single component system, the variance is 3 minus the number of phases. This means that for a single phase system, we have 2 degrees of freedom, typically pressure and temperature. For a 2-phase system, we have 1 degree of freedom, and for a 3-phase system, we have no degrees of freedom. The pressure and temperature are fixed. Despite their simplicity, these systems play a crucial role in understanding the complex world of phase equilibrium. They provide the foundation upon which we can build more complex models, helping us decipher the intricate dance of elements and compounds in the natural world. So, while they may be considered simple, their role in our understanding of the world around us is anything but. What happens when volatiles enter the picture in the study of melt equilibria? Now, that's a tantalizing question. But before we dive in, let's make sure we're all on the same page. Volatiles, in geological terms, are elements or compounds with low boiling points that can readily transition from solid or liquid to a gas. They're often found in the Earth's crust and mantle, and include substances like water, carbon dioxide, and certain sulfur compounds. These tricky little components play a significant role in the geological processes that shape our planet. So how do volatiles affect melt equilibria? Well, think of them as the wild card in the deck. When volatiles are introduced into a system, they can drastically change the temperature and pressure conditions under which a rock will melt. This is because volatiles lower the melting point of rocks, a process known as flux melting. Imagine you're making a batch of homemade fudge. If you've ever tried this, you know that adding a bit of milk or cream, which are volatile ingredients in this context, makes the sugar melt at a lower temperature. Similarly, in geology, when volatiles are added to a rock, they lower the temperature at which the rock melts, altering the melt equilibria. But the influence of volatiles doesn't stop there. They also play a crucial role in the formation of different types of magma. The type of magma produced, whether it's basaltic, andesitic, or rhyolitic, depends largely on the amount and type of volatiles present. For instance, the presence of water can lead to the formation of andesitic or rhyolitic magma, which are more silica-rich and viscous than basaltic magma. In essence, volatiles are the unseen puppet masters, pulling the strings behind the scenes, shaping the very landscapes we see. They influence the type of magma produced, the eruption style of volcanoes, and ultimately, the type of rock formed. Volatiles, though unseen, leave a lasting impact on melt equilibria, molding the very landscapes we see. So next time you marvel at a mountain range or a volcanic landscape, remember the hidden influence of these geological wildcards. Now, what happens when we combine our understanding of phase equilibrium and the role of volatiles? Let's delve into this fascinating interplay. Phase equilibrium and volatiles are two crucial elements that interact and shape our understanding of geologic processes. Their interaction is a complex ballet, a dance of pressure, temperature, and composition that reveals the unseen forces shaping our Earth. Phase equilibrium, as we know, is the state where the properties of a system are balanced. It's like a tightrope walker maintaining a perfect balance. On the other hand, volatiles are elements or compounds that are readily vaporized due to changes in pressure or temperature, much like a magician disappearing in a puff of smoke. When these two elements interact, things get interesting. Imagine our tightrope walker juggling balls, each ball representing a volatile. As the walker maintains his balance, the volatiles are in constant motion, changing states, disappearing and reappearing, all while the tightrope walker maintains equilibrium. In the context of geology, this interaction can lead to some pretty significant outcomes. Take volcanic eruptions, for example. The magma beneath a volcano contains a mix of solids, liquids, and volatiles. As the pressure changes, the volatiles can turn into gas, disrupting the phase equilibrium and triggering an eruption. Another example is the formation of mineral deposits. Here, the interplay between phase equilibrium and volatiles can cause certain minerals to crystallize out of a solution, leading to the formation of rich mineral veins. In both these examples, understanding the interaction between phase equilibrium and volatiles allows us to predict and understand these geologic processes better. It's like being able to predict the next move in the dance, giving us a deeper appreciation for the intricate choreography of our planet. So, studying the interplay between phase equilibrium and volatiles isn't just a fascinating academic exercise. It's a vital part of understanding the world we live in, from the smallest mineral grain to the most explosive volcanic eruption. The dance between phase equilibrium and volatiles is a sight to behold, revealing the unseen forces shaping our Earth. As we journey through the world of phase equilibrium studies and the effect of volatiles, let's revisit the key points we've uncovered. We started by exploring the concept of phase equilibrium, unraveling its intricacies and importance in geological studies. From there, we delved into the realm of simple systems, understanding their role in providing a fundamental understanding of phase behavior. We then turned our attention to the impact of volatiles on melt equilibria, appreciating the significant influence they exert on the melting behavior of rocks. This led us to the intriguing interplay between phase equilibrium and volatiles, a complex relationship that is central to many geological processes. This journey served as a reminder of how each seemingly small piece of the puzzle contributes to a much larger picture. Remember, each granule of knowledge adds up to our collective understanding of the intricate geological processes that shape our world. Thanks for watching us share our videos. Subscribe our YouTube channel and press the bell icon and stay curious for new uploads.